Today we want to talk a little bit more about differential equations, specifically second order linear homogeneous ordinary differential equations with constant coefficients. Normally I don't like to do this simple trick to pass your next test, but if the simple trick leads to something that we can point to and some kind of pattern and it fills in some information for us, then I think it's a good thing. Let's combine some things that we already know. So recall that we can have a differential equation, and a differential equation has an order. So let's say we have an nth order differential equation. The differential equation will produce a general solution, just like the general antiderivative. So this will produce the nth order differential equation standing on its own will produce a general solution with n arbitrary constants. So we're getting this family of solutions with these arbitrary constants. So generally we'll have the same form. So like the antiderivative plus the constants of integration. And we'll have vertical shifts. They come in other varieties, but we'll have all these arbitrary constants. If we want to solve for the arbitrary constants, then we need an initial condition. So if we add to our nth order differential equation n initial conditions, we can use the n conditions to find the arbitrary constants and get a particular solution. So we can use these n conditions to find the n arbitrary constants and find a particular solution. So an nth order differential equation is going to require n conditions because it will produce n arbitrary constants. So we'll need n additional pieces of information to narrow things down to a particular solution. Initially, I said initial conditions, but it just has to be n pieces of information about the function. Could be initial conditions or it could be boundary conditions. Boundary conditions would just be more information about the function at different values rather than the function and all its derivatives at one value, Taylor series style. So the conditions can be either initial or boundary. So that was where we started. The differential equation gives you a general solution. Conditions give you a particular solution, just like when we had finding particular antiderivatives. The general antiderivative had the plus c. If I had a piece of information about the function, an initial condition for the function, then I would be able to figure out what the plus c is equal to and nail things down to a particular solution. The light blue and the orange is very Miami. So what happens in the springtime? The colors start to reflect the fact that maybe I'm already on vacation. Also recall, we solved a first order linear homogeneous ordinary differential equation with constant coefficients. y prime is equal to k times y, and that gave us the exponential function, ce to the kt. C is the arbitrary constant. K is a constant determined by the function. That determines the form of the function, the e to the kt part. C is the arbitrary constant. K is determined by the differential equation. C is the arbitrary constant. K is determined by the equation. So the K is part of comes from the differential equation. C is the arbitrary constant. So here's our general solution. If I have a piece of information like y of 0 is equal to 5, then we're able to solve for the arbitrary constant. So we solve this by looking at it. We want a function where the derivative is just a constant times that function. There are only two candidates. We've got this ce to the kt and also 0. If y is equal to 0, then we kind of trivially solve the equation. But in math, we'll say that's a trivial solution to the equation. We want to call that one out, because otherwise we'll say something like, oh, the only one is this e to the kt, and then someone will be like, oh, but what about y equals 0? And when it comes out like that, I hear, oh, but what about y equals 0? And they're like, don't be a joker, you know that that's trivial. You know what I mean? So it's kind of like when you get into an argument and someone starts making fun of your hair. Then you know you've won the argument because they're all out of things to say. So, all right. So this is what we guessed the solution should look like. We also used a power series to find that the exponential function is the one that we want. But we could find that we got the solution by guessing, looking at the form here and saying the derivative is a constant of what we started with. That sounds like an e to the x function. So note, we got this solution by guessing. Not just randomly guessing. Random guessing is terrible. But guessing is really the only thing that we've ever done. I wonder if this will work. Nope. I wonder if this will work. Nope. I wonder if this will work. Yay. I mean, that's how we learned how to build bridges and stuff like that. You build a bridge and it falls over. You don't think about this and try to solve the bridge problem by not building bridges. You know what I mean? It's like when you're practicing your integration. You don't get better at integration by not integrating things and just staring at the paper, trying to figure out what to do. You've got to start doing stuff. So what we want to do today is bump up our first order equation that we solved just by guessing. It should be e to the kt. And I want to bump this up to a second order equation. So I'm going to do an example. Let's say that y double prime, what do I want? 3 and 4 too close together. 3 and 5 is good. Minus 2 y prime. If I did 3 and 5, I'll have a 15. And I clearly subtracted. So here's a second order, because the second derivative is the biggest derivative. Smallest derivative, biggest derivative? Anyway, it's the derivative. The second order, it's linear because the y double prime, the y prime, and the y are all to the first power. Homogeneous because it's all equal to 0. There's no extra function of x out here. It's ordinary because these are all ordinary derivatives. It's a differential equation because there's derivatives and they're an equation, and there are constant coefficients, 1, -2, and -15. So this fits that description. I'm looking for a function, and I take the derivative, and then the second derivative, and I have to be able to add them all up and come up with 0. This is going to lead us to the same guess that we made for y prime equals k times y. Notice that all the derivatives, the function and its first two derivatives, have to be like terms for this to work. Note. Y prime, and y double prime must all be like terms. Because when we add them up, we come up with 0. This leads us to a guess. We're going to guess that the form of this equation is going to be e to the kt. This is just science. Here's a question. Guess. That's why it really bothered me. There's one scene in Star Trek where Kirk asks Spock to guess. Spock is the science officer. Spock is all about logic. And Kirk asks Spock for a guess, and Spock says he doesn't guess. And I was like, wrong, dude. You are the science officer. All you do is guess. All your knowledge is based on previous guesses. So guess, logic man. I'm not making fun of Spock. Spock's a great character. So we're going to guess that y is equal to kt, and then we're going to take derivatives. So if y is equal to kt, then y prime is k e to the kt, and y double prime will be k squared e to the kt. Once we make a guess, we take our guess and put it back into the equation to see what will have to be to make it work. So I'm going to have k squared e to the kt, that's the y double prime, minus 2 from the equation, y prime, which is k e to the kt, minus 15 from the equation, and then y is e to the kt. All this has to equal 0 from the equation. Now we're going to try to find what has to be true about k to make this equation true. We have a common factor of e to the kt. We should factor that out. And that leaves behind k squared minus 2k minus 15 equals 0. Now things become very clear. E to the kt is never equal to 0. So the restriction, this k squared minus 2k minus 15, this is the part that has to be 0 to make this equation true. So e to the kt, never 0. That part never equals 0. So here is where we get requirements for k that will make the equation work. This right here is called the characteristic polynomial. For the differential equation. And we can see that the zeros of the characteristic polynomial will be the values of k that make this equation work. So our solutions for our zeros of the characteristic polynomial are k, let's see, it's going to be k. Here's what happens when you teach algebra a lot. You can't just write down the solutions, even though you know where you got them. You have to write down the factored polynomial. It's just one of the things. Especially when you start using different signs. If you see me using the same sign a lot, it's because I didn't want to write down the factoring. But it looks like I'm going to need a -5 and a +3. So k equals -3 and +5. So we get these two different solutions to this differential equation. We get two possible solutions. Y equals e to the -3t and y equals e to the 5t. So if we're going to have a solution to y double prime minus 2y prime minus 15y equals 0, it will have to be some combination of e to the -3t and e to the 5t. So solutions to y double prime minus 2y prime minus 15y equals 0 must be linear combinations, there's a new term, of these two, y equals e to the -3t and y equals e to the 5t. Oops. Solutions to this second order equation must be linear combinations of y equals e to the -3t and y equals e to the 5t. What we mean by linear combinations is that constant multiples or sums. So this is a specific term, linear combinations. A linear combination is just a constant multiple or a sum of constant multiples. That's what makes a linear combination. And so this gives us a general solution with two arbitrary constants. Our general solution will be y equals c1 e to the -3t plus c2 e to the 5t. Our second order equation led to a general solution with two arbitrary constants. And two linearly independent solutions. So our general solution, we have two arbitrary constants. We had a second order equation, we expected two arbitrary constants, and we got them. We would say that e to the -3t and e to the 5t are linearly independent because one is not a linear combination of the other. So these two solutions are linearly independent. because one is not a combination of the other. I'll put the other in parentheses. Since there's only two of them, I could have said that one is not a constant multiple of the other, but then that infects the language of linear independence that I'm trying to get. If there were three of them, as long as the third one is not a combination of the previous two, then the three things can be linearly independent. I like to bring this up now because it's spring semester and it's Calc 2, and the next class that I'm going to be teaching is the summer class of linear algebra, and this is an important concept. The idea of linear combinations and linear independence. All right. So what we should expect to see is that if we have a second order equation, we should be able to find two linearly independent solutions. And then so our general solution will have two arbitrary constants as we make a general linear combination of our two linearly independent solutions. If we had a third order equation, we should expect to find three linearly independent solutions. And so our general solution will have three arbitrary constants, three terms, a C1, a C2, and a C3. If you're worried about which one goes first, it doesn't matter. I could have said C2 e to the negative 3t and C1 e to the 5t. That's not important. C1 and C2 are arbitrary. Right. So the interesting thing is that when we have a differential equation of this type, linear homogeneous with constant coefficients, our guess is always going to be the same. We're going to guess an e to the kt. So that raises a and it's going to lead to, that's going to lead to this characteristic polynomial. That's the important thing. We're going to guess an e to the kt, and that's going to lead to this characteristic polynomial. So all these second order linear homogeneous differential equations with constant coefficients are going to lead to quadratic polynomials. And there are three things that happen when we're solving quadratic, when we're looking for the zeros of quadratic polynomials. So we have the second order equation, second order linear homogeneous ordinary differential equation with constant coefficients. Will lead to a quadratic characteristic polynomial. We're going to get, our guess is going to be y equals e to the kt. It's going to lead to a quadratic characteristic polynomial, and we know that there are three things that happen when we find the zeros of the polynomial. We could either have distinct real zeros, we could have a repeated real zero, or we could have complex conjugates. We have to have two because it's quadratic. Quadratic is a second degree polynomial. We have to have two solutions. Could be distinct real zeros. It could be a repeated real zero, or the zeros could be complex conjugates. So I either could have a K1 and a K2. I could have a K1 and a K1, or I could have A plus or minus BI. So the distinct real zeros will factor out. That will be x minus k1. I've been calling, it's fine. And x minus k2. I could have repeated real zeros where the polynomial factors out to x minus k1 squared. Or I could have complex conjugates, A plus or minus BI. Oh, it's not just not factorable. All right. So we've got two other cases to talk about with these second order linear homogeneous ordinary differential equations with constant coefficients. As we'll get a quadratic characteristic polynomial, we've seen what happens with the distinct real zeros. We've got to deal with the repeated real zero. Well, what if we do if we only have one zero that just happens twice? And what happens if we have complex conjugates? One of the things to keep in mind, one of the things that we're going to need is that this repeated real zero, what makes this complicated, I don't know if complicated is really the word. What complicates our situation here is that we need to have a second order equation. We need to have two linearly independent solutions. For the general solution. So that changes how we view this second order equation led to two linearly independent solutions. Now that's not just an observation, that's a mandate. So now I'm changing that up. We need to have two linearly independent solutions to build the general solution. But I can't say e to the 5t and e to the 5t because those are not linearly independent. I can't even just multiply 1 by 10 because they're not linearly independent. One is just a multiple of the other. So hopefully when we get to the complex conjugates one, you can guess what the solutions need to be. Think about a quadratic with complex conjugates, like k squared plus 9 equals 0. Start with something like this and think about what the solutions need. I guess this comes from the y double prime plus 9y equals 0. Think about what the solutions of the y double prime plus 9y need to be, where I have a function and its second derivative are like terms. What function? Think about what functions fit that description, and that will help us then look at the zeros of the characteristic polynomial and then see how that can fit in up here. All right, that's going to do it for today. We'll talk about these new cases tomorrow. Everybody have a good day, and thanks for playing.